Welcome back, deep divers. Today we're tackling one of those questions that really gets to the heart of our fascination and maybe, a little bit of our anxiety about large language models.
Mm,
When you ask an LLM something, is it actually understanding? Or is it just an incredibly sophisticated mimic?
right.
Like when it spits out a perfect quote or gives you this really nuanced explanation, what's really going on inside that digital brain, that tensor field, as they call it?
Yeah, what is the tensor field doing?
Exactly. So we've gathered some really, I think, illuminating sources for this deep dive to explore just that. Is this tensor field, this huge, complex mathematical space where all the learned knowledge is stored, essentially, is it just a statistical shadow?
A kind of echo.
Yeah, like a probabilistic echo of all the data it was trained on. Or is there maybe evidence of something, I don't know, more profound happening?
And that leads to the next question, right? If it is something more, how might we need to design future models differently to really capture that?
That's it.
It's such a critical distinction, isn't it? Because it moves us beyond just looking at what these things can do, which is often amazing,
Impressive.
to trying to grasp how they do it. And,
Yeah.
understanding that how is key for figuring out their real potential, but also, frankly, their limits.
Definitely.
Our sources today, they really push us to look past just, getting the right answer and dig into the actual nature of their, well, what looks like reasoning behavior.
Okay, so let's start there. Let's unpack this idea of the statistical shadow.
Yeah.
Our first source, this is not a library,
Mm.
gives this really vivid, almost poetic description of this internal space.
Mm-hmm.
It calls the tensor field a vast, bizarre construct.
It's a great description. And what's really striking is how emphatically it states there are no stored texts.
Right.
No actual memory, definitely no library like you or I would think of.
Okay.
Instead, all that training data, mountains of it, it's been, well, the source says, digested, dissolved, autopsied by attention. It's broken down and woven into this field.
Wow. So when an LLM recalls something, like a quote, it's not actually finding it.
No, it's not retrieving it. It's performing what the source calls a statistical reenactment. It's piecing fragments together based on probability, sometimes mixing things up a bit, conflating sources maybe.
Huh. A bit like how we might misremember a quote under pressure.
Exactly like that. It's a probabilistic reconstruction, not a lookup.
So less like a librarian pulling a specific book and more like, I don't know, the collective ghost of countless books haunting this mathematical space.
That's a really good way to think about it. The source even talks about pre-training imprinted attractors in weight space.
Okay, what does that mean exactly?
Imagine like deep grooves carved into the model's structure by all that data. When information or activations flow through the model, they naturally follow these grooves, these probability corridors.
Okay.
It's like the ghost of style and form from all the text it's seen is embedded there, not as hard rules, but as statistical tendencies. It guides how it generates new text.
I see. And this idea, this statistical view, it seems to be backed up by other research too, right? Looking at how LLMs actually behave.
Oh, absolutely. That perspective is strongly reinforced. For instance, the Beyond Accuracy survey points out how current models often take shortcuts. They reduce complex, multi-step reasoning problems to just shortcut pattern matching.
So recognizing familiar patterns rather than truly reasoning through.
Precisely. They do brilliantly on problems that look very similar to their training data, but throw them something different and out of distribution scenario, or challenge them on basic logic, math, cause and effect. They often struggle. They make fundamental conceptual errors.
That makes me think of those examples. Didn't GPT-3 and even sometimes GPT-4 have trouble with simple things like logical negation? Or De Morgan's laws, I think. Did that fit here?
It fits perfectly. It absolutely aligns with that shortcut idea. Studies looking at mathematical reasoning show these inconsistencies. Test a model on slightly different versions of the same math problems, and its performance can vary wildly.
Which suggests memorization.
It strongly suggests reliance on memorization and recognizing patterns, rather than a flexible, genuine understanding of the math itself.
Okay.
And you see it in other areas too, like counterfactual reasoning, thinking about what-if scenarios.
Yeah.
LMs often just latch onto keywords, simple lexical cues that trigger a standard response. They don't seem to grasp the hypothetical nature of the situation deeply.
So they miss the what-if part.
Sometimes, yeah.
Yeah.
Or in, say, closed book settings where they're not supposed to look things up, they might even just fabricate facts to make the pattern fit.
Really?
Yeah. So all this evidence, it really points towards their knowledge being this big statistical aggregate, a shadow, like you said, not an internal adaptable model of how the world actually works.
Okay, that's a really compelling case for the statistical shadow view. It makes a lot of sense. But
Yeah.
you mentioned other sources. Is there a counter-argument? Something that suggests it might be more than just mimicry?
Yes, and this is where things get really interesting and maybe a bit more subtle. The paper philosophy has entered the chat. It argues that, okay, yes, LLMs are statistical machines at bottom, fundamentally, but crucially, they are not only statistical machines.
Not only... Okay, what else could they be?
Well, the argument is that something else emerges from that statistical foundation,
Hmm.
especially when you combine it with self-modification abilities and reinforcement learning techniques.
Right.
What emerges are these structures that behave quite a lot like the norms and principles we see in human language itself.
Structures, like internal rules.
Sort of. The paper calls it emergent layered functionality. These aren't just surface patterns. They become, in a way, interdependent and autonomous. They gain a kind of causal power that you can't fully reduce back down to just the raw statistics.
Hmm. Can you give an example? That sounds a bit abstract.
Sure. Think about the rule for using a versus an before a word. An LLM isn't explicitly taught that grammatical rule. It doesn't hear sounds. But by encountering countless examples in its training data, it seems to instantiate this pattern as a kind of broader rule, and that emergent rule then actually constrains its behavior when it generates text.
Okay, so it learns the pattern so well, it becomes like a rule.
Yeah, almost like a principle it follows. The analogy they use is like a flock of birds. Each bird follows simple rules, right? Fly toward the center, avoid collisions, but the flock itself takes on these complex emergent shapes. And that overall shape then influences how the individual birds fly.
Ah, I see. The whole influences the parts, even though it emerged from the parts.
Exactly. It suggests these reusable patterns learned by the LLM get embedded in their own right. They gain a degree of independence.
Okay, that's fascinating.
And there's another paper position, Understanding LLMs Requires More Than Statistical Generalization, that dives into this from a more technical perspective. It talks about LLMs reaching the saturation regime.
The saturation regime, what's that?
It's basically when a model gets so good during training that it achieves near-perfect scores, like
Yeah.
99% accuracy or even higher, on both the data it trained on and new data that looks similar. It's kind of maxed out on learning the basic statistical patterns.
Okay, so it's ace the test,
Yeah.
essentially. But how does that point to something beyond statistics? Wouldn't perfect performance mean it's just mastered the statistics? That seems a bit counterintuitive.
It does seem counterintuitive at first glance, yeah. But here's the twist. In the saturation regime, just looking at overall statistical performance isn't enough. The paper brings up this concept of non-identifiability.
Non-identifiability.
Okay, what it means is you can have two different models that achieve the exact same near-perfect statistical score. They look identical on paper, performance-wise,
Right.
but they can behave completely differently when you give them something unexpected. Those out-of-distribution prompts we talked about, things that are structured differently or are truly novel.
So same score, different underlying behavior on tricky stuff.
Exactly. And this difference, the paper argues, points to something deeper: inductive biases. These are like inherent preferences or tendencies within the model's structure that weren't just learned from the statistics alone.
So the way the model is built, or the subtle things it picked up beyond pure stats?
Precisely. And these biases might be what lead to desirable traits, like being able to extrapolate rules to new situations, or that ability called in-context learning, where it learns from examples you give it during the conversation.
Okay, so it's like, imagine two students get 100% on a math test, but one just memorized formulas for the test questions while the other actually understood the underlying mathematical principles.
That's a fantastic analogy.
The second student could apply those principles to totally new problems, even if their test score was the same as the first student's.
Exactly. The paper actually proves mathematically that this in-context learning ability can be non-identifiable, meaning even models that are statistically almost identical, practically indistinguishable in their overall accuracy, can have radically different abilities when it comes to learning on the fly within a prompt.
Wow. So it's not just about the statistics it learned, but something about its internal structure, its biases.
Yes, it suggests there's more going on than just reflecting the training data statistics. There's some kind of learned structure or bias shaping its capabilities.
Okay, this really shifts things.
Mm.
If LLMs aren't just statistical parrots, but maybe have these emergent properties,
Yeah.
but they're not truly thinking like humans either, where does that leave us for future design? It feels like the current approach might be hitting a wall.
I think that's exactly the implication. And that leads us to the next set of ideas. The paper Beyond Statistical Learning makes a really compelling argument for needing a fundamental shift, a shift away from just optimizing for statistical performance towards something called exact learning.
Exact learning. What does that entail?
It means demanding correctness on all inputs within a defined scope, not just being right most of the time on inputs similar to the training data.
Okay, so 100% accuracy, basically.
Within certain domains, yes. The paper argues that our current obsession with statistical learning paradigms, how we train almost all these models today, is fundamentally mismatched with the need for exactness, especially for things like reliable deduction in science, engineering, or even complex logical reasoning.
Right. For critical applications, mostly right isn't good enough. You need it to be right every time. That sounds like a massive jump from where we are now.
It absolutely is. And the paper shows mathematically why it's so hard with current methods. They demonstrate that even for fairly simple problems, statistical learners can easily pick up those statistical shortcuts we mentioned.
Instead of the real rule.
Exactly. They fail to acquire the true underlying rule, and this becomes obvious when you test them on slightly different data distributions. It suggests that the way we train them now, using things like cross-entropy loss to measure errors and gradient descent to adjust the model, can actually get in the way.
Get in the way of exact learning. How?
It can delay it or even prevent it entirely. They even show scenarios where if a model initially figures out the exact solution, continued training aimed at optimizing average statistical performance can actually destroy that exactness.
Wow. So the training itself can make it dumber in a specific, exact sense while making it better statistically overall. That's quite a paradox.
It is, and it highlights the limitations of just chasing statistical benchmarks.
This connects directly to another source, doesn't it? Theory is all you need. That one really contrasts AI's approach with human reasoning.
Yes, it draws a stark contrast. It argues that AI, especially LLMs, is fundamentally backward-looking and imitative.
Backward-looking.
Yeah, it describes it as a kind of translation generalized technology. It basically mirrors and recombines patterns from its past inputs. It has undeniably a superhuman capacity for memorization.
Definitely sees that.
And it can summarize and rephrase those memorized structures in countless ways. But, and this is the key point, it lacks a forward-looking mechanism or unique causal logic. It doesn't seem to grasp cause and effect in the way humans do.
That thought experiment they used was so powerful. The one about an LLM in, what, 1633?
Yes, trained on all texts up to 1633. If you asked it about Galileo's idea that the Earth revolves around the sun,
It would say no, right? It would support the Earth-centered view.
overwhelmingly so. Not because it's wrong in an absolute sense, but because its entire reality, its truth, is defined by the frequency and probability of concepts in its training data. And back then, the geocentric view was dominant in the texts.
It's trapped by its data's consensus.
Precisely. And that gets to the core of what the paper calls the data-belief asymmetry between humans and AI.
Data-belief asymmetry. Explain that a bit more.
Well, human cognition. Think of the Wright brothers dreaming of flight when all existing data suggested heavy machines couldn't fly, can hold beliefs that outstrip, ignore, and go beyond existing evidence.
Right, we can imagine things that aren't proving yet.
Exactly. That allows us to perform directed experimentation, to generate new data, create new knowledge that wasn't in the initial data set. AI, in its current form, seems stuck with data belief symmetries. Its beliefs are fundamentally tied to and symmetric with the patterns in the data it has already seen.
So for AI to really move towards genuine reasoning, creativity, making actual discoveries, it can't just be a more refined statistical shadow.
It doesn't seem like it.
It needs something more like that human ability for causal reasoning. The ability to formulate new questions, new hypotheses, not just answer existing ones based on past data.
That seems to be the argument. It points towards needing systems that can maybe intervene in the world, conduct experiments, generate their own novel data, systems that possess theory-based causal logic.
And that source, theory is all you need.
Yeah.
It's pretty blunt about it, isn't it?
It is. It explicitly states that human causal reasoning cannot, at least presently, be mimicked by AI systems or computational approaches to cognition.
Wow.
It suggests the future might lie less in these massive, general-purpose LLMs and more in highly customized, purpose-trained, and fine-tuned systems.
Systems built for specific tasks.
Yes, systems that actively incorporate specific theories, unique causal reasoning, data sets, and proprietary documents relevant to a particular field or decision maker to try and push beyond just statistical pattern matching.
Wow. What a journey we've taken, sort of peering inside the LLM's brain. It really feels like we're caught in this fascinating tension. On one hand, you have this incredibly powerful statistical shadow or echo.
Which is remarkably good at mirroring and recombining patterns.
And on the other, these hints, these tantalizing possibilities of something more complex emerging, something not entirely reducible to just stats.
Yeah, I think that's a good summary. The sources suggest that while, current LLMs probably don't understand things in a deep, causal, human-like way, there are definitely emergent behaviors happening that are complex, that aren't just simple statistical reflections. The real challenge now, and probably the focus for the future, is figuring out how to design systems that explicitly move beyond optimizing statistical scores.
Towards that exact learning.
Towards exact learning where needed, yes. And towards deliberately building in those inductive biases or structures that could actually facilitate genuine causal reasoning, maybe even lead to generating truly novel insights, not just rehashing old ones.
It leaves us with a really provocative thought, doesn't it? If we just keep making LLMs better and better at statistical performance, are we actually maybe inadvertently limiting their potential? Are we just trapping them in this incredibly sophisticated cycle of mimicry?
It's a real possibility. What would it actually take? What would it mean for an AI to come up with a truly new idea? A hypothesis that seems, based on current data, almost delusional.
Like the Wright brothers' belief in flight.
Exactly. And then not just state the hypothesis, but figure out how to test it, how to go out and prove it, even if it contradicts everything in its initial training data. What kind of internal structure, what kind of tensor field would an AI need to do that?
That is definitely something to chew on. A very different kind of AI.
Indeed.
Well, thank you for joining us on this deep dive today. Lots to think about. Until next time, everyone, keep questioning, keep learning, and stay curious.